My name is Evan Donahue, as Will said, and I am a postdoctoral fellow at Tokyo College, which is an institute within the University of Tokyo. And my talk today is titled Efficient Variational Inference in Minikanren with Weighted Model Counting. And the goal is to outline a method to extend core Minikanren to handle a useful range of probabilistic programming tasks. In particular, we're going to focus on generative models for things like Bayesian networks, Gaussian mixture models, hidden Markov models, probabilistic context-free grammars, probably with applications to programs and program synthesis, although I'm still exploring that possibility. The paper version of this talk is a bit long and I can't cover all of it here, so my real goal in this talk is just going to be to convince you that with only a few very simple modifications, it's possible to turn Minikanren into an efficient probabilistic programming language that can handle real-world problems. Like many in the Minikanren community, I'm interested in applying Minikanren to problems in artificial intelligence, and it's my hope that this talk can help inspire more interest in exploring uses for Minikanren in machine learning and AI more generally. All the results presented here are part of the small Canren implementation of Minikanren in Pharo Smalltalk, as Will mentioned, which is a fully featured implementation of Minikanren. It's available on my GitHub. The probabilistic extension isn't quite 100% release ready, but it is far enough along to do a number of useful things, so please feel free to check that out if you can handle the small talk, and reach out with questions if you're interested in machine learning with Minikanren more generally. So all that said, and without further ado, let's get into the main body of the talk. Today's talk is divided into three main sections, starting with a naive implementation meant to clarify both the syntactic language extensions that we're going to need and the probabilistic models they express. Next are two sections dealing with important optimizations that target two forms of combinatorial explosion, one involving manipulating Minikanren streams and the other involving tabling. So I'd like to start by describing a naive implementation that is too inefficient to use in most cases in practice, but that can illustrate how to build probabilistic models in Minikanren. So for a simple example, let's consider the case where we have a coin. Let's assume we have reason to believe that the coin is weighted towards tails with a heads probability of 0.25. When writing probabilistic Minikanren programs, we define whatever distributions we're going to need in the host language outside of the run macro. These may be coins, dice, normal distributions, or any other probabilistic object that's supplied by the implementation. A Bernoulli distribution here can be thought of as describing a coin, except it's one parameter, which is the probability of heads. We're now going to flip this coin 4 times, of which 3 are going to come out heads, which is corresponding to the lines that are true here, and 1 is going to come out to be tails, corresponding to the line that's false. And note that I'm using run here and not run star or run 1, and you can just think of this as run star without the reification step. It just returns the stream of states containing the substitutions, the constraints, and so forth, because all the operations I'm going to talk about today are defined in terms of the stream of states, and the reification can be handled later. This brings us to the observe goal, which is the main engine of this system. I'm going to refer to the Bernoulli distribution coin as our model parameters, and more generally, model parameters in this talk is just going to refer to the whole collection of all the probabilistic primitives we define outside of the run statement. Observe is the central interface between our model parameters and the observed data from which we are learning. So each one of these observe statements asserts that we've observed one data point associated with the distribution in question. So one flip of the coin and it came up either heads or tails, true or false here. This program describes our probabilistic model, complete with our prior assumptions about the coin, our observed data in the form of the 4 flips, and a programmatic structure that relates them. So now how do we use this to compute things we care about? For the purposes of this talk, I'm going to focus on 3 common types of probabilistic queries that we might want to use our Minikanren probabilistic model to answer. The first is the likelihood query. Given our prior assumption that this is a biased coin, how likely were we to see those 3 heads in 4 flips? We can use this query to evaluate whether an object like a sentence or a program is likely or unlikely given our model, and potentially even use the partial likelihoods to guide search to more likely regions of the search space in the middle of the run, but that's, again, something I'm still exploring. So mathematically, that's going to come out to be the product of the likelihood of each flip, the total likelihood of the run. It's going to be 0.25 to the third times 0.75 to the first, which equals about 0.011. Now, the way that we compute that in Minikanren is by extending the state with the numeric likelihood score that starts at 1. Every observed statement computes its local likelihood using the distribution and its observed data point, and it multiplies the likelihood of the state by that likelihood. So the first heads multiplies 1 by 0.25, the next by 0.25 again, the tails multiplies it by 0.75, and so on. And the state returned at the end of the run macro then has a likelihood that corresponds to the likelihood of the data given the model parameters, and we can just read it directly out of the state. And to be clear, we are post-processing the result of the run to compute this, as we will do for all the queries. This does not happen within the run per se, unless we, of course, build a run interface on top of run that's also named run, but that's just an implementation detail. So the next type of query that we might want to ask is the learning part of machine learning, the training query. And this query asks, given this data, can we re-estimate the model parameters, in this case, the coin's estimated weight, so that they better explain the data we observed? In our running example, we want to count up the number of heads and tails and divide by the number of heads by the total number of heads and tails to get 0.75, our new estimate. To compute that in minicanron, we need to extend the state again with a dictionary of counts mapping distributions, like the coin distribution, to the sum of their observations, which start at 0. Each distribution, in this case, just our coin distribution, gets its own entry in the dictionary, which may be indexed by a globally unique integer for each distribution, or if the host language supports it, you can use the object ID of the distribution object, which is what I do in Smalltalk. And it actually, to be technically precise, points not just to a simple count, but to a vector of counts. Every observed statement is going to add to the count of the vector of the distribution that appears in that observed statement, and the vector length and the way that it's incremented are specific to each type of distribution and are handled by the distribution implementations in the implementation. So in the case of the Bernoulli, we have a 2-length vector that counts heads and tails. We're going to add 1 either to heads or tails, depending on which is observed. So the first head adds 1 to the heads index of the vector, the second head makes it 2, the first tails adds 1 to the tails vector, and so on. At the end of the run, we just perform the relevant distribution-specific procedure to calculate the new model parameter estimates. In this case, we sum the heads and tails and divide the heads by the result. So far, we've been dealing with the supervised learning case, which is where we have data corresponding to every distribution in our model parameters. We only have one source of randomness, the coin, and every coin flip is observed. I described this as a naive model, but in fact, in many practical cases, namely the fully supervised cases, this is actually both complete and efficient. If we were to build a probabilistic context-free grammar parser, for instance, and we had training data consisting of the full parsers for all sentences, we could run this and it would be very fast to learn a totally functional model of a PCFG grammar. As long as we only wanted to compute likelihoods for fully ground parses, this would be all we need. However, actually using that model to parse new unseen sentences would be a different story for reasons that I will cover when we discuss the tabling optimization. Now, the reason that learning is fast in supervised cases is that there are no non-trivial contees. The data completely constrains all choices, so there's no search actually happening. The implementation just passes once over the fully ground data, counts it up, and does the mathematical optimization at the end. What makes this model naive is when we attempt to apply it to an unsupervised learning problems. And in mini-canron terms, an unsupervised learning problem is any problem where we have a totally free logic variable that we need to observe. And the way we're going to handle unsupervised learning is by enumerating all possible values for these unbound variables using mini-canron and combining all the answer states. So let's suppose we flip our coin, but then on the basis of that flip, roll some dice. If we get a heads, we roll a 10-sided die or a d10. On tails, we roll a d20. And after our roll, we report only the final die roll, not the result of the coin or which die we rolled. So now our problem is not fully supervised. We are not seeing the coin flip, so the heads or tails variable in the observed cannot be bound to anything by the data. And we can express this problem in mini-canron like this. We first define 2 dice as part of our model parameters, the d10 and the d20, using a categorical distribution, which does what you would expect in this case. It just rolls an n-sided die. The real point of interest here is the introduction of Condi. This essentially says we are going to non-deterministically explore 2 paths, one in which you flipped a heads using our previous coin, and then rolled a d10, which came up as a 1, and the other path in which you flipped tails and rolled the d20, which came up as that 1 that we observed. Now let's revisit our likelihood and training queries for a moment here, because now run is returning 2 states. And what we will essentially need to do is combine all of the states returned by run into a single state, and then perform our existing procedures on it. There are 2 basic ways that we can do that combination. We can take the single state with the highest likelihood and throw everything else away, or we can sum all of the states together. Architecturally, these 2 strategies are almost identical, but mathematically, the summation case is more complicated, so I will mostly be focusing on the max case for time in this talk. In practice, it's nice to have both options because they work well on different problems, but we can get started with a totally functional probabilistic programming language, only implementing the easier max case. And that's what I would recommend if anyone wanted to implement something like this, to start with that, because you can always add some in without a great deal of extra work later. So to compute the likelihood, we do what I said, and we find the state with the maximum likelihood, and we just use that likelihood for the whole run. And one thing to note that is somewhat technical, notice that this Conde explores exactly every possible outcome for the coin flip. For the queries I described to be meaningful in this talk, every Conde that returns from answers from multiple branches needs to fully explore some distribution like this. This guarantees that the program describes a generative model, which guarantees that the query's work is advertised. The programmer can violate this constraint in miniKanren, nothing will stop them, but then they will have to interpret the program differently. It's not necessarily wrong, they'll just have to apply a different interpretation to the states they get back and maybe devise different types of queries. So maybe they're writing a non-probabilistic search over probabilistic models, and that's an area I'm still exploring, but there's a lot of possibilities there. In any event, we can still use Conde for normal non-deterministic purposes, or rather deterministic purposes, like iterating over a ground list, which will be the usual pattern for iterating over data points in a data set. So the Conde inside memBuro here, for instance, it's only going to return from one branch since the data set will be fully ground. So this construction is no problem. That constraint about probability doesn't apply here. So back to our training query. Assume we're running this program over a list of data points representing the values of the die rolls. The first data point is going to produce a stream of 2 answers pictured here, one for heads and one for tails. We pick the D10 or the D20 correspondingly. The second data point is going to produce 2 answers per answer for the first data point, because this is a conjunction of Condes. One Conde for each data point, and each data point can join together in the data set. So as you can see, this is going to be exponential in the number of data points, which is why this is the naive strategy. In any case, it will still run, and for the max strategy, we still just pick the single best answer. It contains the highest probability conjunction of heads and tails assumptions for all data points, and we use its counts to compute our new estimates for the coin and dice probabilities. I'd like to pause here and make a couple connections to the underlying probability theory. There were 2 probabilistic ideas that I mentioned in the title of my talk, one of which was weighted model counting. And for anyone unfamiliar with that term, essentially that's just going to refer to the process we've just described. The models are the miniKanren answers returned by run. The weighted models are those answers annotated with their likelihood scores stored in the states. And the weighted model counting is our summing up of the counts from each of those answers scaled by the likelihood scores of those states. And that's a technicality I didn't cover, because for the max strategy, we don't need to weight the counts because we only have one set of counts. But for the sum strategy, we would scale each state's counts by its likelihood and then add them as described in the paper. Happy to talk about it later. Now, we're not quite done yet, though, because with the unsupervised case, unlike with the supervised case, in which we had access to all the data, in the unsupervised case here, we've actually had to just hallucinate some of the data. We just guessed the coin flip for a given data point was heads or tails based on our totally random prior assumptions about the coin. Now, fortunately, the data and our modeling assumption conspired to give us some feedback about whether that was a good guess. For instance, if all of the data points we get are in the 11 to 20 range, we know based on our assumptions about the number of sides on each die that there is a 100% chance those rolls came from the D20, because you can't roll those on a D10, right? And so our coin must be heavily biased towards tails if it's picking the D20 every time. Conversely, if all of our data points were in the 1 to 10 range, we become increasingly convinced that the coin is weighted towards heads, because there are no clear D20 rolls that are showing up as we would expect if it was a fair coin. So as a result, our final estimate of the new coin and dice probabilities are going to probably be better than our original estimate, but since they were based on our original estimate, they might have been better or worse if we'd started from a different prior assumption. And the way that we solve this is with the other probabilistic idea from the title, variational inference, or more specifically in this presentation, the expectation maximization algorithm, or EM. EM is an iterative algorithm, and it essentially just guarantees us, in this case, that if we keep rerunning this training query and are using our new estimates for the coin in each successive iteration, we will eventually get estimates that approach some local optimum and is probably better than where we started. To implement this strategy, we need to extend our count dictionary to hold not only the counts, but also the current estimated model parameters that we reuse in every iteration. So not just our heads and tails counts, but also the current estimated probability of flipping a heads, in our example, 0.25 to start with, which the observed statements will use to compute their likelihoods and which will be updated every successive iteration. Finally, the introduction of Conde here introduces one final query of interest, the expected values query, or in other words, which substitution should we actually use if we're compressing these all to one state, if we want the best assignment of logic variables with the best probability, or the best likelihood rather. The max strategy here is very simple. We just use the substitution that's already in the highest likelihood state that we picked when we threw all the others away. The summation strategy is more complex because we're essentially combining substitutions from different states, and there are a number of ways you could do that. There are a number of different interpretations, but again, I'm skipping over that for time here. And now this completes the presentation of the naive model. It is correct and fully relational as long as you delay observed goals until their observations are ground, which is easy to do with a special constraint. In the next two sections, I describe the limitations of this model and how to overcome them in practice. So as I alluded to earlier, the naive implementation is extremely inefficient. Anywhere there's a conjunction of conds, which will happen in just about any unsupervised problem, it's going to explode combinatorially. So this means at best our runtime is going to be 2 to the n, where n is the number of data points, which is usually large in practice, and more complex problems will have a significantly larger base than 2. So if we're going to use this at all, we need to fix this problem, and we're going to do that with a new type of stream called an aggregate stream. The basic idea that we know at the very end of the computation, at the very end of run, we're going to either be summing or taking the max of our states, either their likelihoods or their counts or their substitutions, depending on our query. Both sum and max are associative operations, so we can cut down on this combinatorial explosion by taking the max or the sum of each data point individually before moving on to the next one. And more generally, we can do this opportunistically, taking the max or sum anywhere we can inside the program, subject to one important constraint that I'll get to in a moment. So now, instead of the first data point producing 2 answers, it only produces 1, its max, which means the second data point, again, only produces 1 instead of 4. So we've reduced the complexity from exponential to linear here in the number of data points. So we are going to accomplish this with a pair of special purpose goals, and I call them maxo and summo here in this talk. They're called argmax and marginalize in the paper. And they replace the condi in cases where we want to make a probabilistic choice of the type I described, so the type of choice that we made when we non-deterministically flipped our coin. So these goals take a distribution, in this case our coin distribution, for an example, an optional logic variable that will be bound to the maximum element in that distribution in case that's what we want, in case we want to use that for something, and a lambda that receives every possible value for the distribution, heads or tails in this case, and returns a goal for each one. And the maxo and summo forms are going to take the goals that lambda returns and essentially disjoin them all together as if you'd written them as part of a giant condi. The condi that this form replaces, complete with inserting implicitly all of the observe statements, so we don't need to worry about observing the value in each branch because that happens automatically to ensure that it's a generative model. And I use the lambda here instead of actually just a condi because it's more general. So for instance, your distribution might be over the English language, and you don't necessarily want to have to manually code a condi branch for every word in English. You might want to look the word up in a table and dynamically generate that goal. I mean, it's your choice, but that's what I would recommend. Now this form is going to behave conceptually the same way that the condi did earlier. It will generate the stream for each possible non-deterministic choice between elements of the distribution, but then it will flatten that stream into one state before returning. In the argmax case, it's going to flatten that the same way it always does by picking the most likely one and returning that. So the important limitation that I mentioned earlier is that by throwing away the additional answers prematurely like this, we are giving up pure relationality. If we decide later that this choice actually should have been deterministic and unify the logic variable with heads, but the maximum value returned by the procedure was tails, we're going to fail. Whereas if we had unified heads beforehand, it would have turned into a deterministic choice, heads would have passed straight through into the lambda, and the likelihoods and counts would all have been modified accordingly. This goal produces a stream that, in the max case, simply compares all answers. It looks like this. I have a first order representation of streams, and that's the one for the argmax stream. Sum is slightly more complicated, but similar. So it's going to compare all answers returned by the lambda's goals, that m plus there, saving the one with the maximum likelihood in that max state variable slot. And it's going to run over all the terms returned by the stream of the disjunction of lambdas, and it's just going to save up the maximum sum, and when that stream finally fails, it's out of answers. We're going to return from here with whatever the max state we've cached is. We're just folding over the stream of answers and taking the max. So that's all we needed, and now we're going to get that exponential speed up anywhere we can safely use this form, which is going to be anywhere we can guarantee that all unifications have happened before calling into this form. We can use it between data points. We can also use it elsewhere, such as on the coin flip in our dice rolling example itself, to pick the best die roll and to throw the other one away, or to sum them together in that case. And here you can see a performance evaluation of a k-means clustering algorithm implemented in Minikanren, which is structurally equivalent to the dice rolling example on a data set of about 14 points, which is all the naive model shown in red could handle before exploding. The aggregated streams and a manual implementation were both immeasurably close in this experiment, so if we just remove that naive one from this graph, we can see that the Minikanren implementation is about a factor of 4 slower than the manual version. Now, the manual version is not optimized terribly well here, and so 4 is probably an optimistic factor in general, but the main point is that it's still the same order of complexity, still linear, and the constant factor isn't so outrageous as to make it impractical. The second optimization builds on aggregate streams by tweaking tabling to make it compatible with this whole scheme. Aggregate streams are more general. Just about any unsupervised problem is going to have conditional independencies between data points, if not elsewhere in the problem that we can exploit using our aggregate streams. Where tabling comes in particularly handy is for reconstructing the standard dynamic programming algorithms for inference in common probabilistic models, like hidden Markov models, probabilistic context-free grammars, and in my particular use case, other related grammar formalisms. The issue is that all of these models depend recursively on subproblems that lend themselves to dynamic programming, without which their runtimes explode. And by caching the answers to these subproblems, as one does in dynamic programming, in a table, we can circumvent that combinatorial explosion. However, we only want to cache the maximal or aggregate values, so that what we're going to do syntactically is just layer the tabled relation right on top of our aggregate stream call as follows. So this is a fragment of an HMM implementation. The details of what the parameters mean aren't important here. I just wanted to demonstrate what it looks like to combine tabling, which is that outer call, directly on top of the aggregate stream we just saw. So there's no real special syntax for it. It's tabling like tabling always is, and aggregate streams like they always are. You just feed a single aggregated value into the table. However, to make it work, we need to make 3 quick modifications to tabling. First, we need to reset the counts and likelihood of any state that enters a tabled relation so that only the counts and likelihoods from inside that tabled relation get cached in the table. So if we don't do that, then likelihoods from whichever state was first into the table, in this case C1, will get cached in the table and pollute all future consumer states, which will get those C1 values they never should have had because they weren't coming from the beginning path that C1 took. The second is to stitch the likelihoods and counts back together when a state retrieves them from the table as a consumer. We just multiply the likelihoods and add the counts of the state calling into the table relation and the cached counts and likelihoods coming out of the table from the table to answer. Now, technically, we have to scale the counts here to handle the sum case, but I'm skipping over that. It's analogous to what we do elsewhere for some cases. It's a mathematical inversion, same architecture. And finally, we need to tweak tabling as implemented in Bird 2009 to make sure it terminates. Aggregate streams wait for their subgoals to fail, but stateful tabled consumer streams never fail. Conversely, tabled producer streams waiting on aggregate streams that never fail themselves never fail, so we can never reach a fixed point. But we can solve this by making tabled consumers fail, and we can do this by having tabled producer streams flip a Boolean flag in the table whenever they fail, whenever they finish producing all their answers and fail, signifying that no new entries will enter their cache. Then consumers, when they see that they run out of cached answers, if they see that flag meaning no new answers are coming, they can just fail directly. That starts the chain reaction that makes everything work properly. However, note this won't, of course, work if there are cycles, but cyclic models probabilistically would require a whole different approach anyway than the one I'm describing, so that's no limit on the expressivity of what we have here. It would only be concerned if we're dealing with other kinds of models we can't deal with anyway, so it's not going to hurt us here. And I'll also add that just as a side note, while implementing this, I found that if you implement tabling with an immutable table and thread it through your search tree in the obvious way that you would do, tabling turns out to be considerably easier to implement than the stateful version. And this integration with aggregate streams in particular is easier as well. I would not recommend trying to integrate it with stateful tabling because it depends on consuming all of its substream's answers. And with stateful tabling, that substream is distributing those answers statefully. And I tried it and I eventually just gave up and rewrote tabling as a result. So that's it for tabling. We can now run with the same order of complexity of the usual dynamic programming algorithms. As you can see here, both the naive aggregate stream and implementations of a hidden Markov model get no benefit from exploiting the dynamic programming opportunity, whereas tabling stays linear. If we table an HMM, we automatically get the Viterbi algorithm with the max goal and the forward-backward algorithm or the Baum-Welsh algorithm with the summation goal. If we table a PCFG, we get implicitly the Viterbi parsing algorithm in the max case and the inside-outside algorithm, respectively, with the sum case. So taken together, everything I've just described yields what has so far proven to be a fairly usable probabilistic programming system. It has held up fairly well, in my opinion, on the types of tasks I've tested it on. What I'm most interested in and what I've only just begun to explore are the possibilities that are opened up by leveraging Mini-Canron's unique properties in a probabilistic context. So I'm hoping others will be interested in exploring these kinds of questions as well, and we'll get in touch and share ideas. So now I'm happy to answer any questions. I'll share my screen.